Okay, so let's see some examples that will give us some more understanding of the definition. And in fact, a lot of things, this structure appears in many settings, not just for random variables, as you'll see. So the first example, of course, is the obvious one. If you're looking at complex value random variables that have a finite moment of every order, there are weird distributions that don't have all moments and so forth, but we are not going to look at them. Right, so this framework only includes distributions with all moments there. So then you can define, so A is the set of random variables you care about, and phi is going to be just the expectation, E, like the general E. And it's easy to see that it's a star probability space, and you can ask yourself questions, whether it's tracial, whether it's faithful. It's all easy and straightforward to check. A more interesting example, especially for us, is when you take A to be the D by D complex valued matrices. Right, so the elements of the algebra are just like deterministic, there are no distributions, right? Just every element in the algebra is a D by D complex value matrix. It's a star algebra, of course. You can add, you can take the products, you have the star operation. But what is the phi here? That's the interesting part. So phi is going to be the normalized trace. Okay, so the trace of a matrix, of course, A is the normalized trace is 1 over D times the sum of elements of the diagonal, but it's also the sum of eigenvalues, not the sum, the normalized sum. Maybe let me denote it like that, of eigenvalues. And you see, even though there is no distribution here, I mean, every element in the algebra is just a matrix, by choosing phi as like that, you can think of the distribution associated with each matrix as the following one. Just sample a uniform eigenvalue from the spectrum, uniformly chosen eigenvalue from the spectrum, right? And that's the expectation that you'll get, right? Because if you're going to sample lambda I with probability 1 over D, that's the expectation, right? So in particular, also phi of A squared, or A to the K in general, that it's a 1 over D sum of lambda I to the K, right? Because that's how it works. Taking the Kth power of a matrix, keeps the same. Well, you just take the Kth power of the eigenvalues, and you see it's consistent with what I said. This is the Kth moment of the distribution that I was telling you about. Right? This is the Kth moment of the distribution that is associated to a matrix, right? Sample an eigenvalue uniformly at random of that matrix. Also note that it is indeed the unital. So phi of 1 is 1, because what is phi of 1? I mean, this one is actually the identity matrix, and all eigenvalues of the identity matrix are 1. There are D of those, so phi of the identity is exactly 1. Right? The normal trace of the identity matrix is 1. Okay. So this is an important example for us because our random variables will be exactly those. After we'll develop the theory, we're going to do everything abstractly for a while, but at some point we're going to consider matrices. And again, it's a bit confusing because there is nothing random about a matrix per se, right? It's a deterministic matrix, but we associate a distribution with that matrix, which is sampling an eigenvalue of the matrix uniformly at random. You can also consider random matrices, and then you have like 2 levels of randomness, sampling the matrix and then sampling an eigenvalue. But let's not do that now. Okay, the third example, and the last example I'm going to give now, is that of a group algebra. It's actually more related to a graph theory than you may imagine. So what is a group algebra? So technically speaking, or informally speaking, actually, technically speaking will come afterwards. Say you have a group, could be finite, could be infinite. And if you want to understand this group, one thing that's general true in mathematics is that you want to kind of linearize it. You want to consider linear structures that are related to the group, right? That's essentially the kind of beginning of representation theory, but the group algebra is a way of doing that. So say you have a group G, then CG, the group algebra of G, is really it's just a vector space over the complex numbers where you think of the elements of G as basis elements of that vector space. Right? So it could be infinite dimensional. Every element in G, little g, is kind of a vector, and you as theoretically, before talking about this algebraic structure, CG is just all finite sums you can take over using basis elements. So this is how it looks. It takes sums going over all the group elements, where every group element that's kind of a vector has a respective coefficient from the complex numbers, but we are going to only consider finite sums. So alpha G is zero except for finitely many little g's. Okay. And sorry. And you take the product as you'd think. So for example, G times H, like 1 times G is just an element here, is the element G times H, right? So it gives you get an algebra. It really is an algebra, C algebra. And you extend that linearly. In particular, I mean that if you take a general element, which looks like that in the group algebra, and another element, then the way you take their product is by just taking all possible, extend linear. You take all possible products that appears in the summons. And if you want, you can collect them back to respect the basis element. So for example, you can ask in this product, what is the complex number that is the coefficient of some k in the group? When if you think about it, it's exactly this thing. It's essentially a convolution, right? It's also actually a star structure. So G star is going to be G inverse, and you extend that linearly again. So a general element like that, when you conjugate a general element, you get this thing. And you shouldn't forget conjugating also the alpha G. And lastly, so that's the star algebra. But what is phi? So phi here is going to be this thing that's usually denoted by tau sub G here, that takes a general element and returns the coefficient of the identity element of the group. Okay, I know it sounds a bit weird when you first see it, but it's actually extremely useful. Okay, so next up we are going to talk about star distributions in the analytic sense, but let's stop here for now.